All right. On the handout there, remarkable connection handout. Yeah, these definite integrals by hand get pretty messy pretty quickly. This first one, I'm just doing the integral of x squared dx. The only one we'll do like this because it's really pretty nice, turns out. If I'm talking the integral from a to b of x squared dx, well, by definition, isn't the integral from a to b of x squared dx equal to the limit into infinity? That's just the definition, right? Well, in this case, f of x, here's f of x, right? F of x is x squared. So, the limit of this sum, the f of x sub i's, is x sub I squared. Now, why am I not using star here? Well, I'm using right-hand endpoints. And if you use right-hand endpoints, your sample points are just x sub 1, x sub 2, x sub 3, right? And so that's why I don't have a star there like I do in the definition, because I'm using right-hand endpoints. And it goes to that. All right. So anyway, I get this limit. Now, the thing here is, delta x is b minus a over n. X sub 1, if I'm going from a to b of my function, I don't know what a is and what b is. I'm just kind of doing this in general. X sub 1 being out here, wouldn't x sub 1 be a plus whatever delta x is? That's all I said right there. It's a plus delta x. X sub 1 is. X sub 2 then, and then which that turns into delta x being b minus a over n, turns into a plus b minus a over n. All right, so if I go x2, well, x sub 2, we just go x sub 1 plus delta x. Well, that turns into this being x sub 1, that's a plus b minus a over n, plus another delta x, which is b minus a over n. So I wind up with a plus 2b minus a over n's, right? Guess what? For x sub 3, I get a plus 3b minus a over n's. So in general, x sub I would be what? A plus I b minus a over n, right? Make sense? Hopefully a little bit. So yeah, whatever x sub I, whatever I is, you take a plus that number I times b minus a over n, because x4 would be a plus 4b minus x5 would be, get the picture, okay? Why do I do all that? Well, that helps us to go further with this. This is just a restatement of what I've got to here. So the limit, so this limit turns into the limit I equals 1 to n of what? Well, if x sub I is this in general, I'm going to say a plus I times b minus a over n squared. That's what x sub I squared would be, times delta x, which is b minus a over n. So far, so good. Okay. Well, turns out, and I've got most of the work here for us. Turns out, if we can evaluate this limit, we can get this integral exactly. That's a big if, though, because that, as you can see, that's a big mess. It's a long thing and it takes a lot of work just to do x squared. But anyway, we can do it. We're going to do it for this one example. And then notice the connection. Okay. All right. Now, so what did I do on line 2 here? Somebody look at it and tell me. Yeah, I've got this. Compared to that, I've got this on the outside. How can I take that to the outside? It's a constant, yeah. The index is I. Does this have an I in it? No. So it's a constant in terms of this summation. Okay? So I can bring this b minus a out front here. And that just leaves me this inside the summation. Okay? Now, guess what I want to do on line 3? I want to go ahead and square that out. Yeah. Go ahead and square that out. It's a plus I, b. All right. So in other words, I'm going to do a plus I, b minus a over n times a plus I times b minus a over n. Okay. Now that's a fun little problem in itself, but here's what you get, right? A times a is a squared. Then you'll have a times I, b minus a, which is ai, b minus a over n. Then don't I have another ai, b minus a over n? So I have two ai's, b minus a over n's. And then what's the last one? Well, that would be I b minus a over n times I b minus a over n, which would be I squared b minus a over n squared. Okay. So I've got the next ones. Is that okay? Is everybody with me on that? All this just comes from that. All right, well, we're getting there. What do I do on line number 4 there? Well, I went from one sum to 3 sums. How can I do that? Well, these are just added together, right? This plus that. And by that property 6, I think it was, we just talked about, I can break those up into separate sums. Okay? That's all I did. I just took each one of these and made its own separate sum. Okay. Well, I would do that because then, what did I do? Well, this one didn't change. What did I do on the second one here? I moved this stuff outside because, again, it's constants. This is a constant, so I can move it out. Same thing here. This is a constant because the index I can bring it out. So far, so good. All right, so that gets us to line 6. If we can scroll there. Thank you, if you don't mind. Thank you. Yeah, good. Thank you. Well, maybe just a little down so I can see that 5th one. All right, there you go. Okay. All right, so what do you think we want to do? Well, turns out, can't I evaluate now these summations by the properties we just talked about on the last handout? What is the sum of the a squareds? A squared n. Because a squared is a constant, right? Yeah, this is just a squared n. Oh, I see I see an error. This part shouldn't be there. Scratch that one. Yeah, because I'm actually going to evaluate these summations now. So scratch on line 6, scratch out that summation symbol. Shouldn't be there. Okay? All right, now, the second one, well, we've got to copy the 2a times b minus a over n, but now I can say what that summation of the i's is. That's one of the formulas. What is the sum of the i's? It was n plus 1 divided by 2, right? And then the third one, we've got b minus a over n squared. And then the sum of the I squares, well, that was just another little formula. It was what? N times n plus 1. Well, right there it is. N times n plus 1 times 2n plus 1 divided by 6. Okay, so we've gotten rid of the sums, which is good. Except I put it in there when I shouldn't have. Okay, sorry about that. All right. So on line 7, just looking to see what I did, on line 7 all I did is went ahead and distributed back in the b minus a over n. I took this b minus a over n and multiplied it by all parts over here. What it winds up being is b minus a over n times a squared n. Then this is 2a. Well, I've got b minus a over n squared then. And then this gives me b minus a over n cubed. That's all I did there on line 7. And then on line 8, well, on line 8, one thing you can do is cancel out the n's right there. So you just have b minus a times a squared. The 2's cancel out here, right, because I got a 2 on the top and the bottom. And that leaves me a times, and I went ahead and did b minus a squared, n squared. And then I went ahead and multiplied the n times n plus 1. And then I just said b minus a cubed over n cubed. Started the multiplying here of this. Multiplied these two out. Okay. Line 9, well, I didn't change anything here. Here, what did I do? Well, all I did here, here's what I'm getting to. I'm trying to do the limit as n goes to infinity. So I just moved this over here because doesn't this kind of look familiar? We've done some evaluating of limits as n goes to infinity of this stuff. Yeah. So I just slid that over there. Same thing here. I just slid the n cubed over under there. Went ahead and multiplied the n inside there. So line 10, what did I do? I didn't change anything here on the first. What did I do here? All I did here was I divided both things by n squared. N squared divided by n squared is 1. N divided by n squared is 1 over n. Same thing over here. Just divided all these by 6n cubed. That gives me 1/3, gives me 1/2, or 1 over 2n, and 1 over 6n squared. With me okay? We're getting close, close, close. All right, now, what I can do on line 11 now is I can actually evaluate all this as n goes to infinity. N is going to infinity, so what is this going to? It's going to b minus a times a squared. N going to infinity doesn't change that at all, does it? So this part just goes to that. There's no changing. What happens on this part? Well, as n goes to infinity, what does this go to? 1 over infinity, which is 0? Yeah. So this part would go to that times 1, which is plus a times b minus a squared. And then the last part is n goes to infinity. Well, that goes to 0. That goes to 0. So this last part would go to b minus a cubed times the third, or 1/3 times b minus a cubed. Yeah. So we finally, that's what you have to do if you're working them this way, is get it to where you can finally do the n go to infinity. And that's getting rid of all the sums. So it's a little bit of work. But there is good news coming. Uh-oh. Oh, right here. Okay, so we've got, what did I do on line 12 here? Well, I distributed the a squared, so it'll be a squared b minus a cubed. Then I multiplied here. Go ahead and square the b minus a out, so I get b squared. Oh, I see what you're saying. That should be minus 2ab, not a squared b. Thank you. Plus a squared. So I went ahead and multiplied b minus a, b minus a. And then if you cube b minus a out, here's what you get. We've done that several times, and that's what you wind up getting. So what do we do on line 13 then? Just go ahead and keep multiplying out, right? So we got a squared b minus a cubed. Distribute that. Yeah, I think I know what I did there. All right, so it'll be ab squared plus 2a, or no, minus 2a squared b. That's where the 2a squared b should have been. Plus a cubed. Then multiply the 1/3 here. That'll be 1/3 b cubed 1/3 times minus 3ab squared would just be 3ab squared. I mean, ab squared minus 1/3 times 3a squared b would be just 1a squared b. And then 1/3 times minus a cubed is minus 1/3 a cubed. So far, so good. We are very close because nice things happen. Very nice things happen. Look at this. Collect your like terms. Well, here's one. Those are gone. Got minus a cubed, got plus a cubed. Those are gone. A squared b. Well, here's one. Here's a minus 2a squared b. And here's a plus a squared b. What happens? Those all cancel out, don't they? A squared b plus a squared b is 2a squared b, but then I've got a minus 2a squared b. Yep. Those are gone. Whoop. Wrong one. And then the same thing happens here, doesn't it? ab squared minus ab squared. What's left? 1/3 b cubed minus 1/3 a cubed. Lots of nice little work. So what do we find here? Well, that's the integral a to b of x squared dx. That's the exact value, no matter what a and b are, that's the exact value of this area under the curve. Wherever you want to take a to b, go from here to way over here, that area right there under that curve, it's 1/3 a cubed, b cubed minus 1/3 a cubed, no matter what a and b are. Okay. All right. Keep that in mind. Let's scroll to the next page. Really keep that in mind. And how much work that was. Flip the page over, and let's do a little more work here. For f of x equals x squared, what's the antiderivative with f of x equals c, with c equals 0? What's the antiderivative? Antiderivative now. The antiderivative, big F of x, remember that's where you do the add the power, add 1 to the power, and then divide by the new power. It's 1/3 x cubed, and like I said, we're going to do c equals 0, because it really doesn't matter what c is in this case. It could be 1, it could be 2, but why not just let c be 0? Okay, now, what would big F of b, the antiderivative evaluated at b, be? Well, plug in b. It would be 1/3 b cubed. The antiderivative evaluated at a would be 1/3 a cubed. Do you see a connection between this and what we just found? The integral we found on the previous page was 1/3 b cubed minus 1/3 a cubed. Yeah, what we've got here, right here, isn't that the antiderivative evaluated at b minus the antiderivative evaluated at a? Isn't that what we got right here for our integral? Yep, that's what we got. That's the connection. Turns out, the integral from a to b of f of x dx is the antiderivative evaluated at b of your f minus the antiderivative evaluated at a. That's what the definite integral from a to b is. They actually call that fundamental theorem of calculus, part 2. I don't think we'll have time to get into part 1, but yeah. Turns out integrals are antiderivatives, basically. if you're called the fundamental theorem of calculus, might be pretty important. And it is. Okay. All right.